Well, I should preface my comments here by mentioning that when I was first asked to do this, I checked with my wife, of course, and she said, no, that's not possible because we have a family event. And I said, but this was very carefully crafted. Chemical cycles shaping the planet, the global challenge. The speakers represented a carefully selected cross-section. And more than that, Molecular Frontiers has a youth forum that introduces the posing of questions worldwide and offers prizes. And she said, well, let me look at the schedule. So she looks at it for a second. She said, I see Thomas, Hoffman, Bai, Arnold, Oliver Satos, Zare, Kroto. She said, you know why you got this invitation, don't you? She said, you have a Swedish surname. So on behalf of my great-grandparents, who indeed emigrated from Sweden, spent the winter of 1853 in a mud hut outside of what's now Red Wing, Minnesota, I accept this invitation. Now, if we look at the title, this is actually brilliantly selected because it's chemical cycles that shape the planet. But of course, when you look at what it takes to analyze these structures in the climate itself, it's a beautiful amalgamation of chemistry, physics, and biology. And the biology, as we heard beautifully described yesterday, is a very delicate structure with hydrogen bonding across the double helix. It's very sensitive to ultraviolet photons. At the same time, developments in lasers and optics are opening up new frontiers for dissecting the fundamental structure of the climate. And this provides a huge opportunity for students to evolve and develop these new instrumentation approaches. And of course, this is a classic link between the molecular level and the global level, and this linkage is a theme that runs through all of this discussion. And in fact, using small aircraft that involve these increasingly miniaturized lasers and electronic systems provide a huge opportunity to answer newly posed questions, and most of the questions in climate change have yet to be answered. At the same time, these instruments can be flown on this aircraft. Now this little guy it's a very small airplane. It has a human being in the left front seat and it has a robot in the right front seat. So it actually doesn't need the human. It can fly anywhere at any time, take off, fly trajectories, land safely, fly for 23 hours out of every 24 hours. This aircraft, on the other hand, while this one can fly 10 meters over the surface, this can fly to altitudes of 20 to 21 kilometers. This aircraft was designed in the 1950s to carry a nuclear weapon in its belly, but we subsume these aircraft and change the color from black to white and apply them to this fundamental question of molecular frontiers as it relates to climate. So throughout this discussion, the way in which new developments evolve and come into play presents a tremendous opportunity for linking very different aspects of science. And it comes back really to the fundamental point that when you try to solve a problem in nature, nature doesn't discriminate amongst chemistry, physics, and biology. It seamlessly links all of them together. So it provides a huge opportunity, I think, for not only restructuring the way we think of research, but also the way we think about courses and structures at universities. So we want to take on this question of the global challenge, and of course, a key center point in this involves the Earth itself. And the first underlying point I want to make is that casting this climate problem in terms of global warming is a profoundly inappropriate description, and you can see immediately why that would be. If I am adding heat to this system and Roald Hoffmann talked about the second law of thermodynamics. I'm going to talk about the first law of thermodynamics and how it's applied to this system. In particular, the first law says the change in the internal energy of this system is equal to the work done on that system by the surroundings or the heat transferred to that system by the surroundings. One is a macroscopic function, the work, which is a force times the distance. The other, heat, is the microscopic exchange through molecular motion or through the transfer of radiation into the system. Well, we only care at this point about the heat term. There is no net work being done by the sun on the Earth, so it's a flow of heat. Now, as we add heat to this system, you can stand back and look and you realize that 70% of the Earth's surface is ocean, and that ocean in many places is 3,000 meters deep or more. It has a huge capacity to take up heat without ever reflecting that in a temperature change. But more serious than that, the very delicate existence of ice systems in the northern polar region and the southern polar region and the Tibetan glaciers, those systems don't change temperature at all when you add heat until all of the ice is gone. So Professor Rosling introduced a new approach, which is to say that when you add heat, you see nothing happening at all until all of a sudden the heat appears and it's irreversible. And that is the key element in what I'm going to say. It's the irreversibility of that system. And since summer is coming, you can take a glass of water, drop some ice cubes in it, put a thermometer in it, and just test this out. You put it out in the sun while you're having lunch, and you'll see the temperature doesn't change one lick until the last shred of ice has disappeared. Then the temperature starts to take off. So we're going to analyze this then in 4 elements. The first is to look at the forcing of the climate and how that changes the heat that flows within the system. Because as goes the heat, so goes our future. And this is the beautiful thing about the first law of thermodynamics. It's really a statement of the conservation of energy, or flipped on its head, it says, we know energy is conserved, so we'd better find out where it's going. And searching for where the heat goes is a lot like searching for where the money goes in a political system. Okay, so forcing the climate occurs by the addition of infrared active molecules, and we'll see what the impact of that is. The second element involves feedbacks in the climate structure. This fact that heat can flow into the system, very little happens until you hit the irreversibility point. And a key aspect of this is one that Sir John mentioned yesterday about the containment of methane within ice structures, or methane clathrates. Now, the methane is inserted into these ice structures by biological processes. They produce methane in anaerobic, that is non-oxygen situations. And these are remarkable structures. They contain an amount of methane 160 times the volume of that ice structure. Now, this happened to be pulled up off the bottom of the ocean about 200 meters down, put it on the deck of a ship, light it, and it flares as the methane evolves off of this and burns. There's twice as much chemical energy tied up in these clathrates than in the totality of all petroleum, coal, and natural gas that's known in the world reserves. This is a very important feedback because as heat flows into the system, it begins to evolve these infrared active molecules. The same is true of carbon dioxide tied up in permafrost. The third element of this involves this exciting new experimental techniques and approaches that we'll talk about very briefly. And element 3 is intimately tied back to element 2 because we can detect very sensitively isotopes of molecules such as CO2 and methane. And the isotopic composition tells us the origin of that methane. We can separate out methane that's formed biologically from methane that's formed thermally in high temperature systems. And we can achieve absorption path lengths 10,000 times the dimension of one of these optical systems. So we can, in a 1 meter cell, we can get 10 kilometers of absorption length. And this is really a capacitor for photons. We use a little quantum cascade laser, and we ring this cavity up, which is the opposite of cavity ring down, which puts in a pulse of a laser and watches it disappear. We ring it up, and then we scan the wavelength of that laser across the absorption feature, and we get beautiful spectral information, but it's very quiet optically, so it has very high sensitivity, very high accuracy, and very high precision. And finally, the fourth element here involves this issue of free radical chemistry, molecular fragments, and the way they play into the catalytic destruction of ozone. And this represents a case and point where we've studied this problem before we began to look at other aspects of the climate. And as scientists, we missed a very fundamental and crucial aspect of the coupling between chemistry and climate that I'll end the discussion with. Okay, so let's look at how this system works. It starts, of course, with the sun delivering energy to the Earth in the visible. And, of course, the sun generates energy by converting hydrogen to helium in the core of the sun at 100 million degrees. The surface of the sun resides around 6,000 Kelvin, and that emits radiation that is intercepted by the Earth. So the sun produces some 4 × 10⁻26 watts of power. We intercept about 5 parts in 10 to the 10 of that. But I'd like to use a unit, the kilowatt hour. It's an extremely valuable unit, a very handy one for macroscopic systems. It's 3.6 10 to the 6 joules. So typically we use joules in the molecular level, kilowatt hours for the large systems. But quite accurately, from the sun we receive 1.5 10 to the 18 kilowatt hours. About a third of that's reflected back. So that produces a net inflow into the climate structure of very close to 1 × 10 to the 18 kilowatt hours. Now, I have to tell a little story. I was testifying in front of a Senate hearing about 2 years ago, and I said, is it all right if I use exponents when I carry out this briefing? And I was told, well, no, these are senators. I think you'd better use another expression. So I said, well, is $1 million trillion all right? And they said, oh yeah, $1 million is the cost of a campaign. $1 trillion is the national deficit. That's fine. So I said, but remember, you have to multiply those two together. Okay. So a year later, I was briefing upper-level individuals in China, and I asked the same question. And they looked at me as though I was insulting their intelligence. And I said, fine, I just wanted to know. But I came away from that realizing that a fundamental problem in information, as Eric Kroto was talking about, resides not with the politicians, it resides with the way universities teach physics and chemistry at the university level. Now, we probably don't have time to go into that deeply at the end, but it's a fundamental problem that is critical to the future of this whole issue. Okay, so we have 1 × 10 to the 18 kilowatt hours per year going into the Earth system. That's balanced by radiating in the infrared, but the radiation comes from a combination of emission from the skin and infrared photons that come out from various depths of that system. But is that spotlight just for me, or? Okay, so the balance then means that 1 × 10 to the 18 kilowatt hours is emitted, but it's emitted in the infrared. So let's cut into this system sideways and look at what this means. So we have our 1 × 10 to the 5. 1.5 10 to the 18 kilowatt hours coming in, a third is reflected back, 1 × 10 to the 18 goes into the system, but the circulating power between the Earth's surface and the cloud water vapor carbon dioxide combination is almost twice that large, and that's a little counterintuitive in the beginning, but you realize that it's the blockage of the escape of that infrared radiation, which is controlled by infrared active molecules, that controls the containment of that radiation, which is the containment of the heat in the system. Very similar to putting on extra layers of clothing. If you took an infrared picture of yourself, as you put more and more layers on, you would see less and less infrared radiation coming out, and you would get warmer and warmer as this process took place. So our issue then is when we add the carbon dioxide to the system, where is that heat going? We know that most of it's going into the ocean, some of it's going into the ice, some into the Earth's surface itself, and some into the atmosphere. But when we start to track this heat down, the best information shows that the oceans are taking up about 6 × 10⁻16 kilowatt hours, hours of energy per year. The ice systems are taking up about 10 times less than that. But it turns out that this is much easier to measure because all we have to do is determine the volume of ice that's disappeared to calculate the heat that's flowed into it, because most of it is almost at the melting point as it is. And this is the issue that I'm going to focus on primarily. Into the Earth's surface, about half of what's going into the ice systems, and into the atmosphere comparable. So this is an area of research that's extremely important because we have to track this flow of heat. So what's the evidence? Here's a satellite observation starting in January of 2007. I'll mention why I picked that. Now we're going January, February, March. We're looking down on the Arctic. Here's Greenland, Scandinavia, coming around the northern United States to Siberia. We're now getting into June, July, August, September. September 16th is the day that these data terminated. This is a microwave satellite that's down-looking that can detect ice very clearly. Now, if I'd showed you the same data from 1955, that ice cap would have completely subsumed the Arctic basin. But more than that, it would be 3.5 meters thick on average. This subsumes barely half of the Arctic ocean, and it's only 1 meter thick. It's average thickness. Now, the Arctic hasn't been ice-free, free of permanent ice, for 2.5 million years. This is the evidence of what heat does, is it flows into one of the most delicate systems, and it initiates an entire range of feedbacks into the structure. And we can go back and analyze from the day that those satellite data were available and track through what happened. And very little happened initially. And, of course, I can go over here and do this all again, back in the 1950s and 1960s, there was absolutely no change whatsoever in the ice until all of a sudden the feedbacks took over, the area of the ice dropped, the volume of the ice dropped, and I can continue to map this out. 2008, 9, 10, it's now down here vacillating back and forth. And the reason why this occurs so quickly and the onset is so irreversible is that once the ice begins to pull back, the oceans begin transporting heat, thermal energy, into the system, which we now define as the Arctic basin. So the inflow of water is now unfettered as it passes between Alaska and Russia and up the side of Greenland. The next thing that happens is that the inflow of atmospheric motion, which normally is cooled by the ice and snow in the basin, it's no longer cooled, so it moves in, delivering a major punch. In fact, most of the energy delivered to the system comes through the atmospheric motion. Next thing that happens is that as the sun shines on the system in the summer, rather than having 90% reflected from ice and snow, 90% is absorbed by the ocean. The ocean is a profoundly effective absorber. So are the trees and vegetation around the edge of the Arctic, and you can see where I'm going with this because a massive amount of methane and carbon dioxide are tied up in clathrates around the edge of the system. The next thing, of course, is that the emission from in the infrared from these systems goes as the fourth power of the temperature. And that means as you drop from a very cold surface to a warm one, there's a tremendous increase in the upwelling radiation, which is now absorbed and re-emitted downward and bathes the entire region in that inflow of infrared radiation. And finally, an effect that's obvious in retrospect that the University of Washington discovered a couple of years ago that is very clear to everybody who swims in cold water, which most of us do, and that is that when the sun shines on water, most of the energy is absorbed in the upper 3 or 4 meters. That creates a warming that decreases the density of the water and locks in a temperature inversion. And so the remaining ice is sitting in that warm pool, constrained by the thermodynamics of the water. So these feedbacks all have come down to bring a recognition that 10 years ago we thought this ice cap would last until the end of the century. 2.5 years ago we thought that this ice cap would last until the middle of the century, and now we know by 2025 there'll be no more permanent ice left in the Arctic. And interestingly, the IPCC, Intergovernmental Panel on Climate Change, published this report in 2007. It received the Nobel Prize that fall, and before the ink was dried on this report, which projected or forecast more ice in the Arctic Ocean at the end of the century than there was the year it was published, you realize how profoundly inaccurate these calculations were. And this isn't a criticism of the people who did this. This is a very difficult thing to determine. They did their very best, and it's the amalgamation of 150 nations working on this problem, so there's tremendous inertia built into it. But it also tells you how potent the feedbacks are in the system, and if they're not intrinsic to the calculation, you can't possibly do the forecast. Okay, so let's look at a crucial number. We know there's about 2 10 to the 18 kilowatt hours per year circulating between the Earth's surface and the water vapor cloud carbon dioxide mixture in the atmosphere. We can quickly calculate how much energy has gone in per year to remove the ice at the rate that's observed. That's 310 to the 13. So this is a very important number. It says that 1 part in 50,000 of that circulating infrared was all it was required to melt the ice at the observed rate. And that tells you how sensitive this system is. Not only the ice in the Arctic, but also the ice in Tibet, that is the water supplies for China and India, and the Antarctic system, that is a very different physical system, but carries the same sensitivity to heat flow. In fact, the West Antarctic ice sheet contains 7 meters of sea level rise. It's protected by a very narrow region of cold water underneath that shelf. Warm ocean water comes in and exits. Very little heat is transferred, but our best knowledge of the temperature structure comes from seals that dive down with temperature monitors strapped to their neck. They come back up and surface. The little device radios this information to a satellite that's collected. That's how rickety the information is. This area is profoundly short on systematic observations. Okay, back to the Arctic basin. We've now looked at the feedbacks that are shrinking the Arctic ice cap. But let's look at the next element, Greenland. Greenland, of course, over time has been protected by this locked-in 3-meter sheet of ice that covers the Arctic Ocean. And of course, I don't have to point out that floating ice doesn't rise at sea level, but when ice exists on the continent, as it does here, 3,000 meters thick at the backbone of the Greenland glacial structure, it matters a lot how much ice leaves the system. So let's take a look at Greenland. Satellite images showed no meltwater at all up until the early 1990s, and then meltwater began to appear along the periphery in the maximum amount of meltwater in the summer. By 2005, the system was showing meltwater all along the periphery, and this is a serious problem because the water doesn't run off like it runs off the back of an elephant. It actually runs down through fissures that are created by the separation of chunks of ice, and it flows down 1,000, 2,000, 3,000 meters to the bedrock, and it's the bond between the ice and the bedrock that retains the horizontal pressure of the structure of the Greenland glacial system. And by breaking the bond, by adding water and decreasing the coefficient of friction, you lose that horizontal retention. It's very similar to a medieval cathedral. It has flying buttresses that retain the horizontal motion. If you pull those flying buttresses out, the massive weight of the center of the cathedral will crush the system as it expands outward. Greenland is exactly the same. It's not going to melt, it's going to decompose. So let's pick on my university. This is the center of Cambridge, Massachusetts. This is the Charles River running through the middle of it. Harvard is shown, the property of Harvard is shown in yellow. Now the medical school is down here. I don't count that yet. So this is the current situation. Now MIT sits right in here. So we have 7 meters of sea level rise from Greenland. Let's add 1 meter of sea level rise. Now Harvard was about to drop $10 billion on a new campus right here across the Charles River that's only 1.5 meters above sea level. Now, the best estimates currently are that sea level will rise by 2 to 3 meters by the end of the century, and that comes out of the latest meeting at the American Geophysical Union. That number, incidentally, was 30 centimeters in that 2007 report. And as you look each year, as more and more information is collected, the degree of sea level rise by the end of the century is building up. So let's add 40%. That's 3 meters of sea level rise. Now, these are called the river houses at Harvard. They're where the undergraduates live. This brings a whole new meaning to the term river house. And the only good news I see here is that MIT sits right here. It goes under well before Harvard. So we're recruiting. Okay. Now, the other issue involves not sea level rise, but the loss of ice systems. And this is what my comments here apply to the Andes, it applies to the western United States, but the Tibetan glacial system is the third pole. It contains a massive amount of ice, and it feeds the Yellow and Yangtze rivers flowing east, and it supplies the rivers to India flowing south. China is slightly less affected because the rainfall in central and western China makes up some of the river flow, but a dominant part of it comes from the glacially fed. So it's sea level, and it is also water supplies. So what do we know from past climate stages? And the reason that this is so crucial is that you hear discussions about plans for burning fossil fuels, particularly with the massive amount that has been discovered through fracking, and fracking brings both natural gas and petroleum. And people talk blithely about this great opportunity to burn this material, adding carbon dioxide to the atmosphere. But past climates have a very powerful message to deliver. And if we look back 40 million years ago, here's an artist's conception, but this is the Arctic Ocean. Fossil evidence is very clear. You know, these old wildebeests, lily pads, turtles, these are all tropical vegetation, tropical animals. There was almost no temperature difference between the equator and the pole 40 million years ago. The oceans were running 8 to 10 Kelvin warmer than they are now, all the way to the bottom of the ocean. And if we map what occurs as we move forward in time, starting 40 million years ago, so this is temperature on the ordinate, this is 0, current mean surface temperature. This is carbon dioxide in parts per million. The weathering of rocks drew down the carbon dioxide concentration in the atmosphere. And as you know, if you put carbon dioxide over water, it's absorbed into the water. That's what carbonated water is. That drops the pH. That increases the acidity of water. So any carbon dioxide that's in the atmosphere produces naturally acidic rain. When that hits rocks, particularly silicate rocks, it dissolves them very slowly and gently, but it delivers that carbon dioxide to the ocean. That's incorporated through the biological machinery into shells. The calcium carbonate sinks to the bottom, and all that CO2 in the atmosphere is drawn down over a period of 30 million years until it bottoms out somewhere around 200 parts per million. Now, when you get to very low concentrations of carbon dioxide, you go into oscillations that are controlled by the subtleties in the orbit of the Earth. The ellipticity, the phase of the ellipticity for the seasons, and that carries you in and out of ice ages. Once you get to 300, 350 parts per million, it's the infrared trapping in that system that completely dominates the subtleties of the orbital variation. So if we replot this, and of course you hear these discussions about using the fossil fuels we have available, and I can tell you we're sitting, as you all know, at 395 parts per million, coming up from 270, and we're coming up through 450, 550, 650. People who have looked at this from a political point of view say there's no way we're going, under the current situation, to control this to levels less than 650 parts per million. So if we plot the carbon dioxide mixing ratio on the ordinate against the change in temperature on the abscissa, we started here 40 million years ago. It takes us 38 million years to bottom out at 200 parts per million. Then we turn the corner, and now in 150 years, we're coming back up well into the period going back to the Eocene. And those glacial structures, when you get above about 350 parts per million, are no longer stable. And the paleo evidence very clearly delineates that. So that brings us back to this question of forcing, the addition of carbon dioxide and methane to the atmosphere. So red is warm. This comes out of the same 2007 report. Blue is cold. So cooling the planet results from the emission of nitrate, sulfate, heavy metal, organic compounds to the atmosphere. And it does it two ways. It produces the normal aerosols that you see in a polluted urban environment, but it also adds nitrate and sulfate to cloud systems, and it forms a much larger number of very small particles, and that has a huge uncertainty associated with it. So this was a typical operating balance between infrared trapping and shortwave rejection, which left us with a net 1.5 watts per square meter of net warming. The problem is, as the research is evolving, this heat isn't showing up in the system. And we now believe we know why, and that is that the uncertainty in the shortwave rejection is way out at the end of the uncertainty bar, and the net result is that there's only about 0.7, 0.8 watts per square meter of net heat flowing into the system. Another way of saying that is that we owe a great deal to China. All of these emissions from coal burning, and that, of course, that includes the rest of the northern hemisphere. Pick on China because it's a particularly important growing component. Same is true of biomass burning. The problem is that we're offsetting a massive amount of this infrared trapping, and if that element goes away, the system will change very, very quickly. Okay, so what drives the demand for global energy? Well, Professor Rosling did a beautiful job of describing the population issue of this. And this is one of the most important back-of-the-envelope calculations you can do. If you multiply population by per capita income and multiply that by energy demand per dollar of output, you can very quickly, in the back of the envelope, calculate the global energy demand. And as he pointed out, the population is sitting at 7 billion, and it's going to 10 billion, so there's a 40% increase in this component. It's this factor that couples population to global energy demand that is really increasing rapidly, because per capita income is increasing, and I loved his graphs yesterday. It shows the dynamic of how that's actually occurring, and it's this term that is driving global energy demand. And if we go back to global population, modern humans emerged about 150,000 years ago in Africa, and I define a modern human as somebody who, if you gave them a haircut, a bath, a toothbrush, and put them in a freshman physics class, you couldn't tell them from the rest of the students, and they'd perform just about as well. That's my definition, and I'm going to stick to it. So life was pretty tough, as we heard. The population just reached 250 million by the Roman period. It hit 1 billion in just about the point of the American Revolution. And of course, this initial increase was a result of agriculture. And then the fixation of nitrogen, as we heard yesterday, drove this up very, very quickly. But the key thing is, what's the energy calculation? When we multiply those two together, currently 15 times 10 to the 12 watts is consumed worldwide in the human endeavor. That's 15 terawatts. When we carry out this nominal calculation, it's about 40 terawatts by 2050. And what does the difference between these two, 25 terawatts, actually mean in real terms? Well, first thing we point out is in 1945, world population of 2 billion, consumption 1 terawatt. That's half a terawatt per billion inhabitants. 2005, population 6.5 billion. That's 2 terawatts per billion people, but we're growing far more rapidly in energy consumption. So by 2050, 10 billion, 40 terawatts is the nominal calculation. So it's this divergence between energy consumption and population. And the fundamental fact to grip here is very difficult, even when you study these numbers, because 80% of our primary energy comes from fossil fuels. So let's just pick on one of them. Let's just suppose it's coal in a coal-burning power plant, but it could just as well be natural gas. A lot of the increase will occur there, and calculate what that actually means. So let's convert that change, 25 terawatts, into what's equivalent in terms of a 500 megawatt power plant. That's the typical size. That's 750 of these constructed every year. That's 2 per day to keep up with nominal energy demand. If it's pumping carbon dioxide into the atmosphere, which it currently is, you can immediately see what's going to happen to the forcing on the climate. If we switch to nuclear, that's 1 gigawatt per plant. That's still 1 per day. And when you watch the machinations that occur around the construction of 1 nuclear power plant, you realize how pathetic that is compared to the numbers here. Now, I'm not advocating either one of these. I'm just simply using it as an example of what this increase in energy actually means in real terms. Okay, so back to our epicenter of the Arctic. We're now going to look at this feedback that's related to the trapping of methane inside these beautiful ice structures. They're certainly beautiful, but they're also potent and important. And the key point here is that once we lose the ice, we start to melt the periphery of the Arctic. The numbers are extremely critical here. So this is the vertical axis in gigatons of carbon. So this is 6, 7, 8, 9, 10. Now, in the talk yesterday by Paul Alvasados, he was using the mass of CO2. So you have to multiply that by 12 over 44 to correct for the atomic weight. So this converts into 30 gigatons per year, 30 times 10 to the 9 tons per year of CO2, but it's typically called out in units of carbon, so it can be applied to other molecules. So 6, 7 gigatons per year. These are the IPCC scenarios. 2006, 2007, 2008, we're going up much more quickly than the upper limit on that forcing term in the IPCC. But a 1% change or 1% melt rate in just Siberia and northern Alaska would add another 8 gigatons to the system. In fact, as we've done more and more research, we realize that it's only 0.5% of that carbon in the soils released as a result of melting would carry us from 8 to 16 gigatons of carbon per year. So this is a really potent feedback. So how can the flux be measured? I'm going to do this very quickly because of time. Again, we come back to these new optical systems that couple miniature lasers to highly reflecting systems. These mirrors, by the way, 1 million photons strike the mirror surface, 1 million minus 30 come back off, and that gives you a tremendous ability to maintain laser intensity inside the cavity and increase the path length. So we build these systems in the laboratory. They are optical mechanical systems, but they're robotic. They have to operate without any human intervention. That has a tremendous impact on the design. They're all computer controlled. It also helps with our laboratory experiments because rather than sitting there and tweaking knobs, we write algorithms so the computer controls the lab systems as well. These are the observations. The laser spools up to its operating level in a thousandth of a second, scans across about a wave number in the infrared, and you can see the beautiful clean absorption lines, and these experiments were done in the atmosphere from an airplane. This is the one experiment that I've built that works better when it's vibrating than when it doesn't, because the vibration takes out the final attempt of the cavity to resonate. And it produces a very fast time response. We run this about 1,000 times a second, a full scan 1,000 times a second. It gives us tremendous time resolution, so we can co-vary the concentration with the measurement of the vertical velocity and measure flux directly. So by incorporating this into a system with the electronics and the software, we fly this on this small robotic aircraft and scan very close tolerance, or in this case over the north slope of Alaska. So this system is just coming online, and we'll be flying this summer for the first time. So now let's track where we are. We have the feedbacks in the Arctic system. We have the feedbacks from the high latitude melting that feeds carbon dioxide back into the system. That changes a large-scale climate structure. Greenland is the next component in the flow of heat that's affected. But I'm going to finish up by talking about a mistake that we've made as researchers, and that is coupling this forcing of the climate into changes in the pathways that connect the lower atmosphere with the stratosphere through convective injection of water. And when we go back to the Eocene, we know that the stratosphere had to be very wet because it's the only way to reduce the temperature gradient between the equator and the pole. The infrared trapping at high latitudes is the only mechanism. We tried everything else. Heat flow in the ocean, none of it works except the trapping of infrared radiation. The Tibetan glacial loss, of course, couples into water systems. So here are some pictures of these mammoth storms that occur in the Midwest of the United States. And we were studying these as a climate problem, both because they're becoming more frequent, but also because they're becoming more intense. And they have the capability of delivering ice crystals to the very high troposphere, the lowest section of the Earth, right to the bottom of the stratosphere. So we were looking at this as a climate problem. And of course, as you read the news, these are becoming a more and more serious problem. They spawn tornadoes and stuff. They have beautiful shapes. Here's an airplane that's about to be consumed by this storm. So we were studying these using this high altitude B-57 bomber, looking at the climate impact through the same kind of isotopic instruments. And isotopes for water become very important because everybody for the last 50 years has believed that air enters the stratosphere in the tropics and it goes through a whole series of cooling events that strip out the heavy isotope. So the HDO isotope of water becomes a tiny fraction of what it is in ocean water. And so you would expect that the water vapor that reaches the stratosphere would be virtually devoid of HDO. That is a straightforward calculation. On the other hand, the other pathway involves the direct intravenous injection of water through a convective event. And of course, as vapor forms liquid, it releases heat, and that heat turns this into a vertical bomb that's moving very rapidly upward. That's the reason we had to use this bomber, because if we flew through one of these things, it would tear the wings off of the U-2 spy plane that we normally use for this, so we use the 57, which is safer. But this is a highly unexpected event that would ever reach above the tropopause. When we were simply investigating the outflow as an infrared trapping mechanism, not a chemical mechanism. But to our shock and dismay, we discovered that this is the isotopic ratio here. These are isotope jargon. Minus 200 means a 20% removal of deuterium. Minus 700 is a 70% removal. So here there's large removal. But the stratosphere in the mean had only a 40% reduction in deuterium. And that meant that a lot of the water vapor getting into the stratosphere is not coming through this temperature-controlled, painful evolution upward, but it's getting in there through direct injection. But in those injection events that we now have seen penetrate 7, 8, 9 kilometers into the stratosphere, there's almost no depletion in deuterium. And that means that that water vapor was injected directly through a convective event. And that brings us back to a picture I never thought I would ever show again, and that's the Antarctic ozone hole. And this is the color rendition. So this is the southern hemisphere springtime result of catalytic activity involving chlorine and bromine operating on ozone, which lowers the ozone concentration to about 1/4 of what it is in mid-latitudes in the southern hemisphere. And this was diagnosed, and I never thought I'd show this one again either, but we used the U-2 spy plane back in 1987 to penetrate through the wall of this polar cap, go into the region that's essentially a chemical beaker. It's completely isolated physically from the outside world. And as the sun emerged over the horizon in the southern hemisphere at the end of the winter, ozone emerges out of the winter largely unscathed. But in a matter of just a few hours, the chlorine monoxide free radical that directly attacks ozone rises to 100 times what the background level is. And then just 3 weeks later, inside this beaker, ozone's dropped by 60%. So that demonstrated through the use of this U-2 spy plane that these two catalytic cycles were the crucial element. And the beautiful thing about a catalytic cycle is that the net impact on ozone in this case results from the cancellation of these reactive intermediates, but the rate at which ozone is converted is equal to the rate of the slowest step in that catalytic cycle. And if we look at the pure chlorine dimer mechanism that Mario and Luisa Molina put forward, you can plot the ozone concentration in absolute measured units against calendar time. We can deliver the CLO concentration directly. We know the reaction rate from the laboratory, and it gives us that slope of ozone. If we add in the bromine cycle of Wofsy and McElroy, which is rate limited by this step, add those two together, it's this dotted line, and these dots are the rate of disappearance of ozone within that chemical beaker. Now, when we testified in front of the Senate, this was the picture that had the largest impact. When you testify in front of a group of chemists, this is the important point, that we understand specifically each reaction, the surface over which it occurs, and the rate at which that occurs. Okay, so then we moved to the Arctic. In fact, the last time I was in Sweden was 2 months in Kiruna, which is north of the Arctic Circle, and here we discovered the same anti-correlation, except from Kiruna we started inside the vortex, flew outside over Russia, back into the vortex. And by the way, this is the first time the U-2 had flown over Russia since 1958, but we acquired clearance to do this. Now, we move forward to 2011, and the largest measured loss of ozone in the Arctic occurred the spring of 2011, where the loss rate was so large that it virtually emulated the Antarctic. And between 2000 and 2011, increasing amounts of evidence came in that it wasn't the ice crystals that were executing the conversion of inorganic chlorine to this reactive free radical form, but it was simple water sulfate aerosols, cold droplets that contained sulfur as the coagulating unit, but were primarily water. And so this all of a sudden changes the complexion of the entire picture, because we had always focused on the cold end at 4 to 5 parts per million in the stratosphere, which is the case we had observed worldwide until we did these measurements over the United States in the summer. And these two lines indicate the transition point wherein when you pass from here, where there's no chemistry going on the surface of those cold water sulfate aerosols, you transition across this point, and this reaction, chlorine nitrate plus HCl, which these two species contain the preponderance of inorganic chlorine, this is a demonic reaction because it ties up the nitric acid product in the liquid phase and it pops molecular chlorine back off into the gas phase. Molecular chlorine has an extremely weak chemical bond. It immediately dissociates and enters into those catalytic cycles. So the point here now we realize is that anywhere in the world, in the stratosphere, where you pass across this, whether you pass across it because of the water vapor concentration or because of the temperature, it doesn't make any difference. It triggers this reaction. So now we look at this catalytic, this water vapor evidence, which we now know is convectively injected, and we just go back and pull out of the record these observations that extend just in the United States in the summer. And these concentrations are 10, 12, 14, 15 parts per million over a very broad altitude interval and over a very broad horizontal interval over the core of the United States in the summer. So if we superpose the observation of temperature and water back onto this plot, the summer water vapor temperature components demonstrate very clearly that this triggers the conversion of inorganic chlorine to free radical form. So this then results in the following. If we do a calculation over just 4 days following the convective injection, this is the mixing ratio in parts per trillion of inorganic chlorine, and typically at these altitudes it's about 1,000 parts per trillion. In the normal unperturbed atmosphere, HCl dominates chlorine nitrate, but going in and out of the daytime periods, right at 200 Kelvin for 5 ppm. So very little happens. I mean, it's a very slight loss of chlorine nitrate, but that's simply a matter of a couple of reaction rate constants. Look what happens when the convective injection of just 12 parts per million goes into the system. In 1 day, the heterogeneous reactions first convert HCl over to chlorine nitrate, drawing NO2 out of the system. Then, the first nighttime period, in the absence of sunlight, the heterogeneous reactions continue to clobber both CLO and NO2, and the CLO free radicals in blue rises immediately, and the dimer also begins to rise, and by the third sunlit period, we now have 400 parts per trillion of CLO, and if we look at 20 ppm, we have basically the same pattern, except it shortens the time for the conversion. So we know that this convective injection put in about 20 parts per million. We visited it 3 days later. It was 12 ppm. And the point is that anywhere in this range, you start taking out a whopping amount of ozone, 5–6% per day. But this isn't over the polar regions. This is over the mid-latitudes in summer. And so I'll just end by focusing now on the coupling between climate and chemistry. And it starts by the release of infrared active molecules, increasing temperature in water vapor as heat flows into the lower system, driving the energy contained in these convective events, which then, when injected into the stratosphere, couple heterogeneously HCl and chlorine nitrate, forming the free radicals that rate limit the catalytic destruction rate of ozone. And this enters not at the peak of the ozone concentration, but on the lower edge. The problem is that as sunlight comes through this layer, typically almost all of the ultraviolet is taken out. And if I compress all of the ozone in the stratosphere into the floor of this lecture hall, it's only about 1/8 of an inch thick. And yet that 1/8 of an inch protects all the DNA, unless you abuse it by going out and getting too much sunlight, not only animals, but also plants, staple crops, wheat, corn, they're all very sensitive to ultraviolet. And speaking from the point of view of the United States, we have about a million new skin cancer cases a year, but the biological amplification factor is almost a factor of 4. That is, you have to multiply the loss of ozone column by a factor of 4 to calculate the fractional increase in skin cancer. So we now have a problem that we consider a significant change in the way we view the coupling between climate and chemistry. And now the last piece that I was going to discuss was the one that Paul Alvasados mentioned yesterday, and that is how are we changing the education in physics and chemistry at Harvard. But I think I have run out of time. Have I run out of time? She said, I'll say. Well, thank you very much.
because we'd like to have some questions. We had to break.
So what about preventing heating and increased cooling of the planet by injecting particles into the stratosphere? Could that be a viable way to save the planet?
Well, I've put considerable time into this question. It's a very good one. So the question is, the infrared trapping that occurs when you release methane or carbon dioxide into the atmosphere has a very long time constant. 20,000 years from now, 20% of the carbon dioxide that we add to the atmosphere will still be in the atmosphere. Carbon dioxide is very robust. So we can't control the infrared side. So the question was, if we are concerned about the heat flow problem, let's block the shortwave forcing from the sun by decreasing the net input from the sun to the earth. This is the question. And there are a number of ways of doing this. One of them, the one originally suggested by Paul Crutzen, was to put in sulfur into the lower stratosphere. And Paul is a very good friend of mine. I have the greatest respect for him. But what this new discovery says speaks very clearly to this problem, because these two lines are actually 1 micrometer squared per cubic centimeter of reactive surface area. This is between 1 and 5. This is the range that you see in the normally occurring lower stratosphere. The solar radiation management or geoengineering plan was to add sulfur to the system, and that would shift these curves out to about 50 micrometer squared per cubic centimeter to get an effective rejection of shortwave forcing. But you can see exactly what that'll do. That will move these two out and reveal the link between the convective injection and the catalytic loss. So it's true we would cool the planet, but the ultraviolet dosage would go up so dramatically that I don't think it would be voted in. But it's a very good question. So it shifts the question from sulfur injection to any other way that you can block the incoming radiation. You can levitate particles in the mesosphere by using radiation to create uplift. The problem with that, though, is it's the acidification of the ocean by continually adding carbon dioxide that very quickly catches up with you. And also the dynamics of the atmospheric motion that generates rainfall, storms, and so on is torqued rather significantly by simply blocking radiation and increasing the infrared trapping. So I've put a lot of effort into this because, as you can tell in the early part of my talk, I'm profoundly focused on the problem of heat flow in this system. It's the greatest problem until we discovered this effect. Now that's checkmate, I think, on any addition of sulfur to the system. And so now we go back. And frankly, I think 350 parts per million is the upper limit to the tolerable amount. And I think the crucial thing now is, how do we safely extract carbon dioxide? I don't think there's any other way out of this. Next question. Yes, Sir John.
Could I receive further clarification about the methane clathrate problem? I feel increasingly disturbed, largely, I suppose, because of ignorance, that as the temperature of the surface of the Earth rises and the stability of the methane clathrate is such that you're going to liberate more and more methane, how serious is this? I mean, there was a time, if I may just ask another simple question, I read somewhere that 55 million years ago, the temperature of the Earth was very much higher than it is now.
Right, that's the Eocene. That was this period I discussed, right.
And, I mean, what happened to the methane then? I mean, there must have been a tremendous amount of clathrate releasing methane. and did not run away. I can't understand it.
Okay, so to answer that question, we have to start 80 million years ago. And the shift in the fundamental structure of the climate, because today we have a very dry stratosphere, that's a climate state that was clearly not the case in the period you were talking about. So if we start 80 million years ago, there was a hypothesis put forward that methane was actually the reason for the water vapor concentration in the stratosphere. So we studied that problem. And first of all, methane reacts with a hydroxyl radical. It has a chemical lifetime of only 10 years. And so between 80 million years ago and 78 million years ago, it would have exhausted all the methane available. So I believe that methane triggered that change. But the minute you have high water vapor concentration in the atmosphere, you relax the temperature gradient, the tropopause over the tropics warms up and water pours in response to the lack of a temperature gradient that creates the overturning rate that drives the adiabatic cooling over the tropics. So I believe what happened was that methane triggered that, but once the stratosphere becomes wet, it stays wet until you draw carbon dioxide out of the system. Now, the first part of your question was, how serious is this? And all I can say is that I voted with my feet. 2/3 of my research group is working on the measurement of methane fluxes coming out of first the North Slope of Alaska and the Arctic Ocean. And then, since we were successful in flying the U-2 over Russia, we're going in to speak to the Russians about studying northern Siberia, because the gold mine of carbon exists in the soils of northern Siberia, and I'm profoundly worried about this problem. And all I can do is commit a huge part of my research group to it.
Could I just add this small point that I made yesterday, that I read somewhere and heard a Japanese presentation less than a year ago, in which it described how there's a major initiative in Japan to try and harness that methane. And this seems to be playing with fire, doesn't it?
Well, quite literally. The problem is it's so diffuse that it's not mineable. It's contained in the upper 3 meters of the soils of the northern reaches of Siberia and northern Alaska and so on, and on the bottom of the ocean. So if you stand back and you look at the inventory of available chemical energy, you come to the conclusion this is a great solution. The only problem is we can't handle more than 350 parts per million in the structure of this climate without completely compromising sea level, water vapor rise. It is demonstrably insane to try to believe we can extract it. And I think you share that. It's really a bad idea. And there are a lot of bad ideas running around.
I think we have to cut here. And let's thank this morning speaker for beautiful presentations.